Okay, let's do it. Hi, everyone. Welcome to the second day of the BHI annual conference. Thank you all for joining us. We're very lucky today to have one of our own PIs, Professor Shing-Tung Yau, who is one of the founding members of this whole field, actually, of mathematical general relativity and the positive mass theorem. And this whole field was very much pioneered by his work in the 70s and 80s, and continuing until today, the quasi-local mass and all kinds of things that we're very lucky to have from Professor Yau. Today, he'll be talking about the existence of black holes due to GR and the dynamics of particles around it. I'm very looking forward to this talk. This is a paper I've had with me for a long time, and it's a beautiful thing that that we're about to hear. So thank you very much, Professor Yau. The floor is yours.
Okay, thank you, Martin. Today I'm going to talk about the works that I did, which lead to some understanding of black hole existence. I should say that I start the subject when I know almost nothing about it, except solving a problem in geometry that we thought is very exciting. When Rick and I did it, and in 1979, after about 6 years working on the positive mass conjecture, and we were rather happy with the geometry behind it. And I was in the Institute for Advanced Study at that time, afterwards, and I attend actually the astronomy weekly lunch seminar. And John Beckall was very friendly to me. But to my surprise, when I mentioned I'm interested in black hole, most of them told me to shut up. He said they don't exist in nature. Since everything in the sky can be explained by Newtonian mechanics. Well, things has changed. Not only that, our colleague found that it's important to set up the BHI, but also two Nobel laureate was given. So I'm very happy to see that things has evolved in a very nice way and has influenced mathematics community very strongly. Many dependent geometers have since interest in black hole and related mathematics. Well, so first of all, we know that black hole was proposed by Laplace a long time ago, but nothing can be done until 20th century when special relativity was discovered, and the geometrization of special relativity, I think, was very important, and it is largely ignored by physicists. Namely, it's due to Minkowski, which really led to a radical change of the concept of gravity, because then we know four-dimensional space-time is important. And this is related to the fact that Newtonian gravity can be explained by this equation, Laplacian U in low, where U is a gravitational potential, and low is a matter density. And Minkowski geometrization says that it should be explained by a tensor instead of a potential. That's a very major change, I think, for the point of view. And then Einstein realized that tensor is important. And this is very important because then you go to 4 dimensions instead of 3 dimensions. And the conceptual change, I think, is extremely important. So Einstein was looking for tensor, and only after his friend Grossman told him what tensor is, he started to understand that's important. And then Einstein wrote down, it was a long history, but Einstein wrote down this equation with some contribution from Hilbert and other people. So this is the Einstein equation, R mu nu minus RU2 T mu nu. This should be looked at as an analog of the Newton equation, Laplacian U. So Laplacian U is second order differentiation of the potential U. Now U is replaced by G mu nu, which is the gravitational potential. And we take second differentiation of G mu nu, that gives rise to curvature. The curvature is unavoidable, actually, because this is the only tensor which is obtained by differentiate G mu nu. And the right-hand side is the replacement of the load. So it's replaced by energy stress tensor. So the Einstein equation is very natural because of that. And this is actually exactly what Einstein described himself, how he discovered the Einstein equation. It relates gravity with matter similar to Newton's equation. And in space-time, particles with mass travel along geodesic, which are timeline, while photons travel along non-geodesic. And Einstein's equation shows that the Ricci curvature of the space-time metric accounts for matter distribution, but the content of gravitational force rests on the full curvature tensor of the metric. So that's how things come out. And the left-hand side is not exactly Ricci tensor. It's more than Ricci tensor. Is the subtract out the R2 G million. This left-hand side was actually discovered by Richard in 1900. This is also observed by Richard that this is a tensor which is conserved tensor, set by conservation law. So Einstein actually did not realize that it was discovered earlier. Anyway, so this is important. And from here, we want to discuss how things goes. The first important solution in Einstein equation, as we know, was due to Schwarzschild. He assumed symmetry, spherical symmetry, and write down solution to Einstein equation. And this is a famous Schwarzschild solution where there's a singular point when R equals 0, and curvature goes to infinity there. The problem is that physical law cannot be interpreted as such a point, classically. Well, since there's a large group of symmetry, most people do not believe that singularity should exist in nature, and the many physicists challenge that until the great discovery by Roger Penrose in 1965. And I guess Martin has talked about it yesterday, so I would go through it a little bit fast than what I'm supposed to do. So he reinvented the concept of closed trap surface. It's a space-like two-dimensional surface so that the light ray cannot be escaped from there, roughly speaking. And this we define to be a black apparent horizon. You take union all closed trap surface around the black hole. We call it apparent horizon, a black hole. So Penrose proved a remarkable theorem that exists a closed trap surface implies space-time is incomplete. The proof is completely geometric and using some elementary topological argument, but it's rather spectacular that he will think about this problem already in those days. But the singularity he proved is actually quite weak. He just proved that there exists geodesic which has a finite n. And this was generalized further by several people, and Martin has talked about the history, so let me not worry about it. So the important point is that Penrose found that the closed trap surface is Schwarzschild. Therefore, whenever space-time is closed to Schwarzschild, singularity will therefore persist to exist whenever space-time is closed to Schwarzschild. So we know that singularity cannot be perturbed away anymore. But it needs to explain how closed trap surface can arise in general space-time and by what mechanism. So that's a question that I come up with Rick Stern later. So, so the important feature of gravitation is that it's unstable when there's very large concentrated mass. This was already found by Chandrasekhar in 1925. A star mass greater than about 1.3 times that of the sun, which has exhausted its resources of thermal and nuclear energy, it cannot sustain itself against its own gravitational pull. So the gravitational collapse will happen. But the final stage of the collapse can be a neutron star or some other sub-objects. It need not be a black hole. However, the existent closed trap surface should lead to a more serious singularity, which is believed to be a black hole. And if we consider the Penrose conjecture, cosmic censorship is true, we believe that it must be a black hole. But these are a much more difficult problem that needs to be proved and addressed to. And I think Martin has talked about it somewhat yesterday. I believe personally a curvature singularity will occur, but Penrose and Hawking cannot prove that. It would be very interesting to see generically curvature singularity will occur. And so now I want to go to demonstration of existent closed trap surface under general physical principle. of accumulation of matter. And this argument is rigorously done, and no symmetry assumption was assumed, and no special equation of state for matter is required. So many people wrote about such questions related to this, assuming the fluid dynamics satisfies some equation of state and all that. But here we are talking about very general conditions without any assumption. So formation of trap surface due to mass condensation. That's what we did in 1983. So let's formulate the statement a little bit more precisely. First of all, in space-time, we don't have a global time function, but nevertheless, we still define it. So it is kind of hyperbolic, assuming the space-time. And the induced metric on this space-like hypersurface would be positive definite, and it's Gij we call it. And we have a dGij over dt as defined on the hypersurface. The reason is that we are dealing with a second-order hyperbolic system. Einstein equation is such an equation. So the initial data consists of two parts. One is the initial data, one is the time differentiation of it. So Gij restrict to n and dGij over dt restrict to n. Therefore, are the initial data, but because we require gauge independency, so it reduced to a pair. Gij and Hij, where Gij is the induced metric on n, Hij is the second fundamental form of the space hypersurface n in space-time. So this determines the space-time in the neighborhood if we are dealing with a vacuum solution when there's no matter whatsoever. It determines uniquely a time evolution in the small. The global behavior of the evolution, on the other hand, is the most challenging problem in general relativity, as was shown by the special solution of Einstein equation given by Schwarzschild. Singularity are unavoidable. And I will call a singularity caused by closed trap surface to be a black hole type. This was consistent with the cosmic synthesis that Penrose proposed. So let's say what we are dealing with. In case we are not dealing with vacuum, so more than vacuum, that means Gij is no more zero. Then we need more than just Hij and Gij. If we choose E0 to be normal vector to n in space-time, E1, E2, E3 are tangential to n, then the Gij has several important components, which we call mu, which is the normal component, and TCOI is Ji. So these are local energy and local linear momentum. It defines a 4 vector as is observed by the local observer sitting in n. And in general, we will assume something called dominant energy condition. So mu will be bigger than or equal to square root of summation Ji squared. So there are 4 equations governing Gij, Hij, mu, and Ji. These are called constraint equations. So the initial data formulation of Einstein equation basically tells you we want to look at these 4 quantities and see how the space-time evolve out of these 4 quantities. Now, a closed surface is called a plane horizon if the mean curvature of sigma is equal to trace of h on sigma. These are called closed trap surface. This is a way of formulate the definition of closed trap surface, which is called marginal trap in the formulation which Martin talked about. So let me not explain in too much detail. But anyway, existence of such a surface will give rise to a geodesic incomplete space-time. So we call such a surface a black hole as a definition. So up to now, we still use this as a definition for most people. Well, sometimes you want to use the event horizon, but event horizon is way too complicated. We have to know too much about the future in order to define what is the event horizon. So we use this. And we have to assume that the space-time is asymptotic to trivial space-time, namely Minkowski space-time, where we will assume Gij looks like Euclidean metric at infinity when R is very large, and Hij does not fluctuate too fast, define big O 1 over R squared. An important reason to assume Hij goes down fast is that we have to define some quantity which converge, like the mass, total mass, and the total angular momentum and all that. So these are important four of conditions that we have to make assumption to. Now, when we have such a behavior that R is large, when we are far away from the center, the mean curvature of the surface, two-dimensional surface, is bigger than trace of H, because H goes down very fast. The mean curvature goes down like 1 over R. So that's an assumption that we know. And so given a region omega in N, so that this mean curvature is bigger than this, that's assumption. Rick Chen and I studied the following equation. This equation is an important mean for us to prove existence of the black hole. So, so I say it here. I take a graph of a function defined on omega. So omega is a function, and the graph is x comma fx. In the product space omega with R, there's a mean curvature. We set this equation to be mean curvature equal trace of that. So this equation is very similar to the equation that the apparent horizon, the black hole solution here, which I write down mean curvature equal to trace. So I write down generalizing that to 1 dimension higher. So the black hole existence was proved by looking on a 1 dimension higher space-time, namely the product space or omega with R. So what this equation was actually solved, well, not solved, was studied by physical Zhang, but he abandoned it because he said there's no solution generally, so he wanted to giving it up. However, Rick Chen and I make use of it because we have been studying mean curvature equation for a long time before we come into this problem. So we like it. We observe a very important statement that it implies existence of black hole. So the general statement is that if the matter density is bigger than some positive quantity in a fixed radius, so lambda is, you can scale it any way you want. If the radius is big enough and the density is large enough, a black hole forms. So notice in this formulation, a black hole existence has nothing to do with the equation state or symmetry. It just exists. So this was done in 1983. And the way that we prove it is actually interesting. We want to look at this equation, the graph equal to trace. As I said, the equation actually does not have global solution, F. We perturb the equation plus epsilon F. We prove that when epsilon is positive, a global solution exists. And then we found out when epsilon goes to 0, epsilon may not converge and blow up vertically along some surface sigma in omega. The amazing thing that we found is that the sigma actually forms a apparent horizon. It becomes a black hole. So black hole exists due to this high dimensional equation. And when epsilon goes to 0, it comes out. And this is very important because we can prove all the apparent horizon appears in such a way. And in fact, the way that we prove this has some interesting because recently many people try to generalize the concept of more global condition on the dominant energy condition. So mu minus j bigger than equal to lambda bigger than 0 was used actually to demonstrate the first Dirichlet eigenvalue or an operator, which is a Laplacian operator plus scalar curvature over 2. We proved that the first eigenvalue is at least lambda under the assumption of matter density. And then based on this assumption on the spectrum, we proved the radius must be less than or equal to something unless a black hole exists. And this contradiction comes from the existence solution, therefore we prove. So the process of proof black hole existence actually go through some spectrum argument. And so let me show you a little bit differently. The equation I wrote down actually has this form, which says divergence of some vector is equal to right-hand side. And if I integrate the right-hand side over a region, over any subregion, we get this inequality, which says that if the Hij is bigger than some lambda Gij, and you take capital lambda to be the mean curvature minus lambda, which means two principal curvatures together, is satisfy this inequality. And this number 1 is true. And this says that as long as the sum of 2 eigenvalues Hij is large, then a black hole will form. And this is a different way of looking at the assumption that I make. So in fact, it says the following thing. If I look at the operator is defined to be L. LF to be d over dxi, lambda inverse d over dxj. So lambda, remember, is the density that I was looking into, the matter density. And if the operator has non-negative eigenvalue, then it gives a sufficient condition for the existence of the black hole, the negative of the first eigenvalue. So previously, I used matter density to prove existence of black hole, but in fact, you can replace it by global condition, namely the negativity of the first eigenvalue of some operator. So I hope this will be closer to quantum gravity, but it's far away from that. But it's interesting, I think. Anyway, if we don't use a matter to prove existence of the black hole, we can change it to some condition on the boundary of the black hole, which I will not go into. Now, in a recent work with Chen, who is also with PHI last year, we consider the following problem. We look at a metric, we're coupling with Clyde-Gordon equation to first order form. And we prove that we can decouple it to form an equation of this form. And we can prove the following thing. We look at the equation I wrote down earlier to existence, proving the existence of black hole. And I deform it, put an epsilon there, and take limit. And finally, we prove that the initial data, if it contains an apparent horizon, then U must converge to U epsilon will converge to a function U, which U equals 0 and somewhere. And this defines a apparent horizon. And what is the whole point here is that we can solve the equation, at least in the case of spherical symmetry, and it has an elementary solution. The whole point here is that we can prove that the initial data can exist non-singularly, and after a short time, it becomes singular. Not singular, it becomes a initial data with apparent horizon. So what does this whole thing mean here? It means the original formulation that I did with Richard was static in the sense that a black hole forms when matter density is large. Here, the thing that I did with Chen says that the original data could be non-singular with no apparent horizon, but then the apparent horizon will form after time t, which depends on some initial data, which I will not go into detail. So that means apparent horizon can be formed dynamically also, not just statically. And this was studied by Christodoulou and many other people, which I don't have time to go into, but Martin did talk about it somewhat yesterday. So you can also formulate the dynamics of Einstein equation using the formulation that Richard and I use. Now, Martin also talked about this yesterday, so I didn't have time to talk about it. You can generalize some of the works that we did here. Now, I promised to talk about particle moving outside black hole. So as you know, you have this picture, and the Event Horizon Project has found the shadows of black hole, and also, and there's a great work by Andy and his whole group with Alex going to talk about a little bit later about the photon cell. But on the photon cell itself, there's a following structure found mathematically by my colleague, Mr. Xu, who is sitting next to me in Beijing, in Tsinghua University, using KAM theory, which is an important theory, of course, KAM theory. So you just study the perturbation around the K metric. So K metric is this form with delta and all that here. And if it given a particle moving around, there's a particle energy E, and the C component of the particle's angular momentum, Q is a Carter constant related to theta, and the total Hamiltonian will be minus half for time-like geodesics. So we look at the geodesic behavior of particles near the black hole, K black hole. The photon cell will be union bound spherical orbits unstable under radial perturbation, and the cell consists of slices of spherical orbits with constant radial component. The radial instability is measured in the following way: it's exponential divergence, and The photon cell is surrounded by bright ring as observed by the event EHT. And it was discovered by Andy's group that this ring has an intricate subring structure whose size, shape, and thickness can be used to prove the geometry of black hole.
It wasn't my group, Yao.
Well, anyway, your whole group is about okay. Anyway, Alex will,
people did a lot.
Alex will explain to you, so let me not get into it. Okay, so light ray getting exponentially close to the cell will complete n half cells, and hence collect n times more photons along its path, and you get sharper and narrower and brighter when they're put in the cell. But what Mr. Xu, well, here is the thing that I guess Alex will talk about, so let me not talk about it. But what Mr. Xu talk about is this: on the photon cell decay, each spherical orbit has a latitude frequency omega theta and oscillating around the equator, and omega phi when rotating around the black hole. So these two frequencies has a ratio. These are KAM theory. If the ratio is a diphonic number, so a number is called diphonic number if there exists a constant c and tau, so that this thing occurs. X minus p over q is bigger than equal constant, q to the power 2 plus tau. There's a full measure set of numbers that are not well approximated by rational numbers. So this appears in Moses and KAM theory, so it's very important. And Mr. Xu looked at this and found out the spherical size is robust and the orbit is still quasi-periodic. And if it's not diphonic numbers, the orbits are broken and chaos occurs. So it's very interesting. As a result, that gives a gap structure on the photon cell. Each gap corresponding to a ratio, rational ratio nu that we wrote down there, the omega theta, omega phi. The larger the gap, the smaller the denominator occurs. And there's Arnold diffusion according to here. Generic perturbation of integrable system can create orbits with big oscillations of some conserved quantities. And the Arnold diffusion for perturb care, there exists an orbit which looks like the following picture. So it's a beautiful picture, and I assume that you probably can see it in the sky with observation, and it starts to have occasional expression along the homoclinic orbit. It's interesting chaotic phenomena. So in the case also, when the massive particle energy is equal to 1, there's an orbit, there's an analog of Kepler's parabolic orbit, and the perturbed K has an orbit of oscillation type. So supremum can go to infinity, the distance, and the infimum is bounded. So you keep on going back and forth. And this, in the case also, near the outside event horizon, the radial component is regular, then you have an interesting chaotic phenomena again. So you can observe chaos around the black hole, and hopefully this can be seen in the sky. So the work was published in the archive, so you can take a look at it. So I think time is up for me, so I will stop here.
Well, thank you very much for a beautiful talk. So let's take questions. Please raise your hand or just.
Yeah.
Yeah, Andy, you have to unmute.
Is it possible that what would you actually see up to this chaos and the gap in the Kerr orbit? What would you see if you looked at the sky?
Oh, I don't really know. I mean, this here follow the general theory of KEM. I assume you can see some stars which are moving around like that.
Well, there is chaos in dynamics of objects in astrophysics. So this is just the chaos in the photon orbits. That's all.
Yeah. But anyway, there's a rather rich theory around for KEM, and he's adapted to the case also. And I think there's something needs to be studied in more detail.
Yeah, thank you for this great talk. I have a simple math question. When you consider the geodesic equation in pure Kerr, yeah, which is an integrable system, then mathematically you shouldn't say there is chaos, right? Even though the orbits in the exact Kerr, the orbits that go around this photon shell they can end up going anywhere, and they're exponentially sensitive to initial conditions. But that's not technically chaos. You need to perturb Kerr to get mathematical chaos.
Perturbation. KM field is starting near after you perturb. There's invariant tori, and there's some path between the invariant tori. Only after perturbation you get a chaotic phenomenon. Small perturbation.
And this KEM theorem, it gives you some percentage of the invariant tori that get destroyed as a function of the size of the perturbation?
Well, it depends on C and tau that you see here. In this approximation rational number, the diphonic number says x minus q over q bigger than equal C divided by q to the power 2 plus tau. The tau and C give you some different levels, right? The gap structure corresponding to a rational ratio nu. The nu is omega theta omega phi. That one has we said is a diphonic number, and then the spherical cell is, you know, quasi-periodic and all that. So this gap structure relates to this C and tau. When you change C and tau, there are different structures changes. Okay. So it's interesting to see what happens when you move from C and tau to different C and tau, and see how it goes. Okay.
Yeah, it would be interesting to see if we can connect this to some observational signature.
Right, I think that's interesting. So I suggest you to read this paper and see what we can see in terms of observation in BHI.
If you perturb Kerr a little bit, you know, if you have some gas around it, so it's not exactly the Kerr, you know, not exactly the Kerr solution, do you expect the photon shell still to exist?
I guess I think that's what we are talking here. There's some part which remains, some part is chaos, and
right.
so that's what it is supposed to be. So it'd be nice to see what happens in sky, whether this comes up in that way or not. So you don't exactly see Kerr, you see something similar that looks like this, because it's a small perturbation of Kerr.
So, Professor Yau, I have one question. So you mentioned a result with Chen about somehow prescribed initial data without apparent horizon, then form of apparent horizon later. I want to ask how general is the initial data? Was the initial data close to the spherical symmetrical case? Or yeah, I want to ask the question.
I do not quite understand. You are talking about the my lectures about the black hole?
I'm asking your result with your recent result with Chen in your talk. You mentioned. Right. I'm asking for the initial data. How general it is? Would it be close to spherical symmetric case or yeah? It
is spherical symmetric we are dealing with there, but the data we have to fine tune it, and then you can find such a thing. So apparent horizon will form after finite time.
Oh, you mean close to spherical symmetric data?
They're spherical symmetric data.
Spherical symmetric data. I see.
But,
okay.
But I think the argument holds without with small
perturbation. I see.
The conclusion is independent of spherical symmetry. But in order to create the assumption that we like, we have to calculate, and the calculation is based on spherical symmetric data.
I see. Understand. Okay. Yeah. Thank you very much.
But all the arguments are general. I mean, we don't argue only on spherical symmetry. That's a nice thing about this argument. It's very general argument.
Right. Okay. I see. Thank you.
I found that it's interesting about using some operator eigenvalue to try to understand. I don't know because recently a lot of people talking about how to change the energy condition instead of pointwise non-negative, and then we can use this spectrum. But this may not be physical, but I still like to see what the physics behind it, because we can use it to prove existence black hole and some positivity conclusion. Okay.
Thank you. Yeah.
If that operator has a negative eigenvalue, does that mean that some field on the background will have an exponentially growing mode?
I guess you can formulate in that way, but we don't argue in that way. I use the dimension reduction. Eventually, I use this one to reduce to Stanley wheel operator to make conclusion. But I think one can try to interpret in terms of exponential growth of some eigenfunctions. You know.
I mean, it looks kind of like it looks sort of like is this the same as the scalar wave equation? Would there be an exponentially growing mode of a scalar, or?
Well, as I said, I didn't argue in that way, but I can try to do it that way. The argument was based on dimension reduction, which I'm rather proud of, because it's actually, I say one of the ingenious, after 30 years looking back at it, that I can do that.
So Andy, it's an elliptic operator. So I don't think it's like the wave operator.
No, well, elliptic
No,
operator,
but it would tell you it's not the wave operator, but it's on a slice. It's on a space-like slice.
Sure,
So
sure.
it might mean that the d by dt squared of, if f is a scalar field, d by dt squared, it would be more interesting if there might be some spin 1 eigenvalue, right? You could, because there's photons in the real.
Yeah. Yeah, I think it would be interesting that, Andy, you can give some more inputs. I think about it, because I do think this operator should have some meaning physically, and hopefully change it to make it to be more interesting.
Well, we had some, of course, the way that was originally proved, you know, where if the stress tensor is too big in some region, the stuff you did earlier, that of course is exactly what we expected from physics.
Right.
It's hard to imagine there's some statement that is this universal that doesn't also have some physical origin. I'm trying to think what it would be.
I try to formulate it in a more general way. I think eventually I may formulate it in a more physical way. Right now, I'm just struggling to formulate it so that it's good. But there's only one formulation for some special case. I hope maybe Martin could look into that we can formulate it in a more general manner. Okay. Because I was written actually in the other day, last week, about energy condition. And seems to be too complicated for me to formulate in this way. But I hope some kind of energy condition in quantum gravity can be interpreted. So maybe Andy, you can help. I don't know.
Another issue is a higher dimensional version of the original argument. That's something that Professor Yau was, I think, one of the things that you mentioned to me quite early on. So I've been thinking about this as well. Yeah. And I think something can be done there as well.
Right. Well, it would be nice to have more physicists to come in to look into that. I think that would be interesting. Well, that's a good thing about being shy, that we can talk to each other.
Yeah, one question about this Arnold diffusion. I don't quite understand it, but it seems related to energy extraction from the black hole. So a really interesting question is if this Arnold diffusion prefers the perturbed particles to escape near the poles.
Interesting thought. Yeah, that could be.
Because I think it's a phenomenon. I'm not sure I understood correctly, but I think it's a phenomenon whereby you perturb the Kerr geodesic equation, and then you can modify the dynamics of the particles. And if they prefer to escape near the poles, I think they extract energy. So it would be interesting if there were a connection to jets.
Oh, yeah, that should be related to jets. I think KMP is related to jets. Yeah, so it's a good point. We'll look into that. Thank you.
All right, everyone. We have to be pressing on a little bit. Are there any final questions?
Can I ask?
Yeah.
A comment, question. So first, it seems to me that there should be critical photon orbits even for a perturbed Kerr black hole, just by continuity, because we know we have orbits, if we shoot them from infinity, we have orbits that fall inside it, orbits that fly off to infinity. So there have to be some critical ones in the middle. And also, I mean, it would be maybe interesting to relate that to gravitational wave signatures and their electromagnetic counterparts. Like you can imagine like a perturbed Kerr black hole, and then you can see some gravitational wave signature of some plunge, and then relating that to a change in the photon ring.
Yeah,
signature.
that sounds interesting. Yeah, we will look into that in more detail. Yeah. Yeah, thank you.
All right, everyone. I'm afraid we have to be pressing on. We have a schedule, but let's thank Professor Yau one more time for a beautiful talk and some very exciting work. All right, so Hsin-Yu, your slides. Can you share screen? Hi, there we go.
Okay.
Let me know when you're ready.
Sure. Hold on. Can't find my mouse anymore. That's fine. Can you see my slide?
Yep.
Okay. Yeah, great. So, yeah, let's start.
Okay. So, welcome to everyone to the second talk of this morning. We're very lucky to have Hsin-Yu from MIT and the Kavli Institute. She was a BHI member before, and we're very lucky to have her speak on the following topic: can standard sirens resolve the tension in the Hubble constant? Take it away, Hsin-Yu.
Thanks, Martin. So yeah, hi everyone. Thanks for having me back. It's great to be with this crowd again. And so yeah, I moved to MIT, but I still work on similar things as before, which is gravitational wave astrophysics and cosmology. And today I'm going to talk about whether this standard siren, which is a way we use gravitational wave observation to measure cosmological parameters, whether this method can help us to resolve the tension in the Hubble constant. So very quick with this so-called tension in Hubble constant. So to describe the universe expansion history, we can relate the distance to an astrophysical object, or to be more specific, the luminosity distance to an astrophysical object, which is dl on the left-hand side in this first equation, to how fast these objects are flying away from us due to the universe expansion, which is the redshift, or z on the right-hand side here. And to relate these two quantities, we can use a set of cosmological parameters, which is on the second equation here. There are h0, which is a Hubble constant. There are omega matter, omega lambda, etc. And all these parameters help us to describe the expansion history of the universe. And as you can see, h0 serve as a fundamental parameters for us to describe it. And that's why it's very important for us to determine it. And there are already many experiments trying to figure out what h0 is, but the problem is that the measurement from early universe, for example, using the cosmic microwave backgrounds, the measurement from there are inconsistent with other experiments that are done based on more local sources. For example, the type 1a supernova, which is on the right-hand side on this plot. And as the precision of these h0 measurement getting better and better over time, the tension between this early and late universe measurement become bigger and bigger. So there are several approach trying to solve this tension. For example, one group of people try to come up with new physics to explain the difference. Another group of people try to figure out whether we have some unknown systematic in the current experiments that's already been done. And the third group of people, including Dom, and also myself, is that we try to see if there is other independent measurement of Hubble constant that can be done. And these measurements are precise enough and also accurate enough for us to say something about this controversy, especially if you want this new method, no matter which new method is, you want it to be to help us to say something, then you need the precision of this measurement to be better than the tension, to be smaller than the tension that is already shown there. And one possibility turns out to be this gravitational wave standard siren method. So there are some reason why this is actually a method that the community is trying to pursue, including that it is considered relatively straightforward, relatively clean for when we compare it to other methods. And you will understand why people have that feelings as I explain what it is. So coming back to this relations of distance and redshift, to determine the cosmological parameters, we will need both the measurement of distance and the redshift. And from the gravitational wave, we actually directly obtain the distance to the gravitational wave source. The distance goes inversely as the amplitude of the gravitational wave signal. Of course, there are some other parameters also affect the amplitude of the gravitational wave signal, including, for example, the mass of the systems, or what is the viewing angle of your systems. And among these other parameters, for example, the mass of the system actually can be determined by other part of the gravitational wave signal. We can determine it by how the frequency of the gravitational wave signal evolve over time. So these parameters can be independently determined. However, some other parameter, for example, the viewing angle, or you can call it the orientation of the system, that's just the same thing, they cannot be very well constrained. And that's why they actually contribute a lot to the uncertainty of the measurement of the luminosity distance. And we actually will come back to this later. So from the gravitational wave side, we have a very straightforward way to determine the distance. The other quantity we need to determine is the redshift. And Avi already briefly mentioned this yesterday. It is very difficult to determine both the distance and redshift independently from gravitational wave, like solely from gravitational wave observation. There are several possibilities, several methods, but all of them are very challenging. So there are actually other ways that we can actually try to use the help from electromagnetic wave observation. So the idea is the following. The gravitational wave signal, these systems, they come from some galaxies. They all have their host galaxy. Maybe over time they propagate out to the outward or even further away from their host galaxy, but their host galaxy should be somewhere somewhere close to them. So if we can determine which galaxy it is, then we can measure the redshift of the galaxy. Then we can use that redshift to do this standard siren method, to do this standard siren measurement. But in reality, LIGO Virgo are not very good at localizing the gravitational wave sources on the sky. The way we localize it is actually, we say that they lie within certain uncertainty volume on the sky, and that volume is very big. So within this volume, there can be a lot of galaxies, and you don't know which one is the real host galaxies. So that would cause a lot of confusion. And that's why we actually need the help from the electromagnetic observation. If this gravitational wave system, they also emit light, and these light are captured by traditional telescope. These telescopes are doing much better job than the gravitational wave detector to determine the location of the source on the sky. And therefore, they can help us to determine which exact host galaxy it is, the source come from. and then we can get the redshift and measure the cosmological parameters. This method has already been realized from the first neutron star merger observation by LIGO Virgo. Here is the event. At the tip of this red arrow, that is our event. We got the distance from LIGO Virgo. The big blob next to it is its host galaxy. We have a redshift measurement of it. Then combining both, we obtain the first H0 measurement. The solid blue curve here is the posterior of the H0 measurement. It has a big uncertainty, but this is only a measurement from single event. Our expectation is that in the future, we will have multiple detection like this. And the upper panel here, I'm showing the expected number of this kind of detection as a function of time. And then the bottom is the corresponding Hubble constant Hubble constant precision from this event. And actually, when we did this projection a couple years ago, we were using our best guess of how often these neutron star binaries merge over in the local universe. But actually, after the latest LIGO Virgo observing run, we found out that the actual rate for this merger are not that often. So the real projection probably lie at the lower end of our projection, in which is on the red arrows I'm showing on the plot there. So overall, it seems that no matter what, even if the astrophysical rate are going to be low, that means it's gonna take a slightly longer time for us to achieve a required precision of Hubble constant. When we have about 50 this kind of binary neutron star observation with electromagnetic counterparts, we will achieve an H0 precision that may help us to say something about H0 tension. So that's great, and we can actually do it. We can actually improve the precision even better. So one way to improve the precision is very straightforward. We can try to look for other kind of gravitational sources that also emit light. For example, the merger between two black holes. So in the past, it was in the past, we thought that this kind of stellar mass binary black hole system, it is very difficult for them to have gas around them, and therefore they are not considered, we don't consider them emit light in any way. However, one of the latest event, this is a binary black hole merger. There's a telephone number, GW 190521 there. This one, the telescope ZTF, the team ZTF, they actually found a potential electromagnetic counterpart associated with it. And one possible explanation for this electromagnetic counterpart is that these black holes, they actually merge in the accretion disk of an active galactic nuclei. And there are a lot of gas around, and these black holes merger, they could basically stir the gas inside the disk, and in the end they emit light when the black holes merge and then kick out from their original position. So suppose this electromagnetic counterpart candidate is actually real, then we can do exactly the same thing I just described. We can conduct the standard siren measurement, and that's what we did here. So comparing to the original measurement of H0 with that single neutron star merger, that gives us a gray line here. After we combine this extra binary black holes merger, we obtain the dark blue curve here, which give us better H0 better H0 precision. It's actually also getting closer to the Planck value, but still too early to say. But in general, if we have this kind of event in the future, then we will be able to achieve a better precision faster than we expect. Another way to improve the precision of center siren, we can is to ask like what contribute most to your uncertainty of H0 measurement. And it turns out to be you are not able to measure the distance very well from the gravitational wave side. And the reason that we cannot measure the distance very well is because of this so-called distance inclination degeneracy. So what it is the following. For a binary system, say the one on the left-hand side with their rotational axis in parallel with our line of sight, which is what we call the phase-on binary. When we compare the gravitational signal coming from this kind of system to the right-hand side system, which their rotational axis is actually perpendicular to our line of sight, or so-called edge-on binary. If everything else is the same, then the amplitude of the gravitational signal coming from a phase-on binary will be larger. And the reason for that is because the gravitational wave emission from a binary system is actually strongest along their rotational axis. However, if we push this phase-on binary further away, then the amplitude of the gravitational signal when they arrive at our detectors, they can look exactly the same as an edge-on binary that's close by. And that's why if we don't know the viewing angle or the inclination angle of the binary, we will not be able to determine the distance very well. That's again where we can try to use the information from electromagnetic observation again. So here is an animation of the electromagnetic emission from a neutron star merger. The elongated jet there, that represent the short gamma ray burst. And for this kind of short gamma ray burst, we already have various observations in the past. Those observations suggested that these gamma ray bursts are narrowly beamed. They beam within a southern cone. So the emission from the system is not isotropic. It is actually very narrow. It actually has a strong structure. Another type of emission from a binary neutron star merger is the kilonova, which is a thermal emission. And this kind of emission is more isotropic than a short gamma ray burst. However, they can still have structure. And these structures are unknown yet. We will need more observations, more simulation as well to really determine what kind of structure it is. So this part is actually highly unknown. But no matter which one it is, we do know that the electromagnetic counterpart are not isotropic emission. And that also means that we actually can use some model to interpret the electromagnetic, the EM observation we got. And then we can use that to reconstruct what is the viewing angle of the system we have for a given event. So here is a simulation. Suppose that now we do have this kind of information. So as you can see, the horizontal axis, I'm just showing you 1,000 simulated event, and I'm showing you the fractional uncertainty on the distance measurement for these 1,000 simulated event. And we start with, there is no extra information from electromagnetic observation at all. Then the uncertainty lies around, say, 20%. Is actually highly scattered. But if we start to have some constraint coming from the EM observation, then depending on how well you constrain the viewing angle, that sigma iota on the right-hand side, that they are just showing you the uncertainty of your viewing angle measurement, then you will be able to push this uncertainty down by a factor of 2 to 3. And actually, this factor of 2 to 3, you can interpret it directly as a factor of 2 to 3 improvement in Hubble constant measurement. And if for individual event, we have a factor of 2 to 3 improvement. Then when we combine event, the uncertainty goes as 1 over root n, where n is total number of detection. Then that means with a factor of 5 to 10 fewer events, we will be able to reach the same H0 precision we require. But now you can ask one question, because I already mentioned that to have this extra constraint on the on the viewing angle from electromagnetic observation, you actually need some model to interpret it. What if your model is wrong? What if do you have a bias there? It actually can cause a lot of problems, and that's what I explore here. Let's say your viewing angle inferred from the electromagnetic observation is actually biased, depending on whether you underestimate the viewing angle or overestimate the viewing angle, which is on the left and right hand side here. Your resulting H0 measurement can be terribly biased. So in the simulation I conduct there, I started with an H0 value of around 67. But if you do have some bias in the viewing angle, you can have a very big bias on your H0 measurement, as I show here in the blue band. And I found out that you actually need to control your systematic in the viewing angle to be 10 degrees or even less to ensure that your H0 measurement is accurate enough. So then you can ask the next question. Okay, if it is so difficult, and if it's difficult to constrain your viewing angle from EM observation, it's difficult to control the systematic, then fine, we can just choose not to use those information. And turns out, even if you don't use that extra information from the EM observation, the fact that your EM emissions has structure, that means you can actually preferably observe the system from certain inclination angle. Let's say you might be able to capture the EM signal from the binary if they are face on, then edge on. That's just as an example. So if you do have this kind of selection over the binary viewing angle, when you combine all these binary mergers and you try to conduct this H0 measurement, you will have to correct for this kind of selection effect. In this case, it's a selection over the viewing angle. But the problem is that we don't have a good idea of what is the exact structure of this EM emission from binary merger. So we don't know how to accurately correct for this selection effect. And here I'm showing you how big the problem is. So here I'm just exploring how, let's say you can only, I just assume that you can only observe the binary from 0 degree, which is entirely face on, to an opening angle of say 10 degree, which is a very strong selection because you can only observe it within a very small cone on the left hand side here, or all the way up to 70 degree, which is a much weaker selection. And again, I start with a simulated value of say around 67. Then if you do know what kind of selection effect it is, then you can nicely reconstruct your injected or your simulated value. But suppose you don't know what exactly the selection is, you can easily have an injected value of 67, which is closer to the CMB value, but you end up with the value that's closer to the type 1a supernova measurement. So this is a problem we have to actually solve, and it's not solved yet. We will need more theoretical calculation and also more observation to help us to reconstruct the structure of the EM emission from binary merger. And finally, we can compare this new systematic I identified to other systematic, the other non-systematic for the standard siren method. And it turns out this new systematic actually can be larger than any other known source of systematic for the standard siren method. So it actually can dominate the systematic for standard siren, basically. So back to our first slide, or my title, can we resolve the H0 tension with the standard siren method? The answer is possibly, but already we have no issue for us to explore and try to find a remedy, basically, for all these lists of systematic before we can really say anything solid about the H0 tension. And I guess I'm actually over time, so I'm gonna leave us here at the summary. And thank you for your listening. Question.
Hsin-Yu, if we approach the precision of 1%, one should keep in mind that it corresponds, 1% of the speed of light corresponds to a few thousand kilometers per second, which is also the kind of the maximum recoil speed that you can get for a black hole remnant as a result of a collision, or any other merger. And so I was wondering if we knew the correct cosmological parameters to that precision from other techniques. And instead of trying to constrain cosmology, we were trying to learn something about the source that previously we couldn't. So the redshift that appears in the chirp mass may be different than the redshift of the galaxy because of the recoil, for example. But there could be other things that we can learn. Did you think about that?
So actually there was a work done by Sylvia and also Vijay Varma in the past. So what they can do is that we actually can infer the black hole recoil velocity from mostly from the merger and post-merger part of the gravitational wave signal. So that actually can give us some idea of how fast that is. For binary neutron star merger we are considering here, that might be more difficult because we don't have that part of measurement. We don't have the post-merger part of measurement with current LIGO Virgo sensitivity. But surely if we have 2.5 G, so maybe 5 years from now, the sensitivity will improve and we will be able to constrain that part of, say, recoil velocity, although actually no one have done that yet for the binary neutron star merger. Binary black hole, yes. Binary neutron star merger, not yet. So if we can get that part of information from the post-merger, then we might be able to actually even resolve this degeneracy or figure, like take this contribution out from the redshift measurement we have.
Yeah.
And so yeah, I did think about it, but we just cannot do it right now.
Needless to say that you constrain also theories of gravity that are not the GR to very high precision as well. I mean, at the level of 1%, because you're using a different messenger.
Yeah.
All right. Are there any other questions? No one is raising their hand. I can see in the chat.
Erwin is raising the hand.
Ah, Erwin. Yes, please. So you're muted, Erwin. We can't hear you.
Okay, got it. Now
Yeah.
you hear me?
Yes.
Yes, sorry. Is it too naive to think that you could assume a uniform distribution of the unknown angle of the binary with respect to your line of sight? And so if you have many observations of different ones, you could average over them and get a reasonably accurate result. Is that too naive?
So it is naturally we do have a uniform distribution of the inclination angle. But the problem is that the probability of capturing different inclination angle are not the same, both for gravitational wave and electromagnetic wave. So that's why there's a selection for the population we can use for the standard siren.
Thank you.
Gary Melnick has a question.
Can you hear me?
Yes, we can.
I may have missed this, but your estimate of a 1% precision on the measurement of H naught, is that per gravitational wave detection, or is that assuming co-averaging many?
It is combining many. So yes, go ahead.
So I guess my question is that I was intrigued by the suggestion that perhaps there is no deep physics discrepancy between the CMB measure of H naught and the more local supernova measurement of H naught due to perhaps the clustering of galaxies at the lower Z's that the supernova measurements are made. So I guess I'm just wondering if you've thought about the need to carefully segregate the measurements that you derive per gravitational wave determination of H naught on the basis of distance.
That's a very interesting idea that I did not think about, but I can see that our future detectors, which will allow us to observe the binary merger at higher redshift, will allow us to segregate the population and see if that really, if we really see a difference for the local and the higher redshift populations.
Thank you.
All right, so I think it's time to close this morning session. We have to press on with our timetables. So we'll be reconvening at 10:30. Apologies, that only gives us a 20-minute break. 11:30, excuse me, for Jamee's talk. All right, everyone. See you soon. Hello, everyone. Can you hear me all right? Yeah. Okay, good.
Yes.
Well, I hope that the 20 minutes of break was well spent and that you're fully refreshed. We'll get on the way. So welcome to our second session of the day. We have Jamee Elder, who is a BHI postdoc, who will be speaking on the epistemology of multi-messenger astrophysics. And we will have questions at the end as usual. People can raise their hand or unmute. And Jamee, take it away.
Okay, thank you for that introduction. Yeah, so today I'm going to be talking about the epistemology of gravitational wave astrophysics. And now I'm not exactly sure whether that's sort of a philosophical term of art. So for anyone who doesn't know, epistemology is basically the study of knowledge. So when I say I'm going to be talking about the epistemology of multi-messenger astrophysics, I'm interested in the kinds of inferences that can be made on based on multi-messenger observations and basically how good they are. That would be the epistemology. So this talk is going to be a little bit of a shift from some of the other talks we've had, in that I'm going to be talking about some general philosophical issues concerning the methodology and epistemology of astrophysics. I'm also following along from Hsin-Yu, not going to be talking primarily about black holes, but rather about this particular event, the first detection of gravitational waves from a binary neutron star merger. And of course, the coincident electromagnetic signals that allowed for so many exciting new pieces of science to emerge. So here on the slide, I've just got a quick summary of the observations that came about as a result of this one event. For this audience, I'm not going to go into too much detail of the physics because most of you will be familiar with a lot of this. But just in quick summary, the observations that I'm going to be talking about today include both gravitational waves, this GW 170817, as well as a wide range of electromagnetic observations. So the gamma ray burst 170817A, which arrived at the same time as the gravitational waves, as well as the follow-up campaign, which resulted in a wide range of electromagnetic radiation, including the kilonova and delayed X-ray and radio counterpart. So in quick summary of what I'll be talking about today, I'll start off by talking about what I'll call the epistemic situation of gravitational wave astrophysics. What I mean by that is basically the challenges that characterize this as a field of science. I'm then going to draw some comparisons between astrophysics and the historical sciences, things like geology and paleontology. Although this might be on the surface kind of a surprising comparison, there's a lot of similarities between astrophysics and these sciences, both in terms of the challenges they face and some of the kind of methods of argumentation that are employed in each. And then finally, I'll turn at the end to some sort of more philosophical upshots. Okay, so first up, the epistemic situation of gravitational wave astrophysics. So the key question I want to ask—
sorry, Jamee, there's some background noise happening. So whoever it is, can you mute yourself? Or maybe, Jamee, is your microphone near your hand or something?
Possibly. I'll try to avoid that, but
yeah. Sorry to interrupt, please.
No, not a problem. Right, so the key question I'm going to be interested in here is how multi-messenger observations, that is messengers with, in this case, both electromagnetic and gravitational wave signal, how does this change the overall epistemic resources of gravitational wave astrophysics? How does this sort of change the toolkit that's available for astrophysicists in this field? So to begin with, I'll just briefly talk about some of the challenges of gravitational wave astrophysics in general, with a particular mind towards the majority of events, which are binary black hole mergers. So for a start, gravitational wave astrophysics is in its infancy relative to electromagnetic astrophysics. And this is not intended to be a slight towards gravitational wave astrophysics, but rather just a statement that it's relatively new. And when you're doing sort of frontier science, inevitably, you're facing sort of different challenges than in more established fields. So part of this is that gravitational waves are weak and difficult to detect, thus only detecting them in 2015, whereas of course electromagnetic radiation to some extent we can detect with our eyes. Gravitational wave detectors are also far less established than, say, ordinary telescopes. There's just much less of a history of experience with them, sort of less opportunities to iron out the wrinkles. And of course, the theoretical grasp that we have on solutions to Maxwell's theory outstrips our theoretical grasp of Einstein's theory. And this is particularly important in that gravitational wave astrophysics relies on having models, especially of the late stage of a compact binary merger, in order to both detect gravitational waves and to make inferences on the basis of the signal. And so recent progress in understanding and developing models of these dynamical processes is really important for being able to make accurate inferences in gravitational wave astrophysics. Now, another challenge, which I talk about in other work, which I've presented in the BHI Philosophy Foundations of Physics seminar, which I won't talk about too much today, is that there's a kind of epistemic circularity problem that arises here. Now, part of this is due to the fact that gravitational wave astrophysics is probing new physical regimes, so the dynamical strong field regime, where the final stages of a binary black hole merger. And this is the kind of scenario where it's possible that the descriptions offered by general relativity might break down. Now, whether or not you think it's plausible that this is the case, it remains that gravitational wave observations are sort of our first empirical evidence for or against this being true. So in advance of the observations, we don't have empirical evidence either way. Now, the methodology of gravitational wave astrophysics relies on having accurate models of target systems in these new regimes. So what you end up with is a situation where, to some extent, your observations are reliant on having accurate models of these systems in these new regimes. And meanwhile, in order to validate those very models, you're reliant on the very observations that you're doing. So there's a sort of circularity problem here, which isn't, of course, to say that this is an insurmountable problem, but it's certainly a problem that gravitational wave astrophysics has to meet in order for us to be confident about the inferences that are being made. And another key challenge is simply that, look, we're doing astrophysics. So a lot of the sort of experimental methods for overcoming these kinds of challenges are not typically available. So no manipulation or control of the target systems is likely to be possible. You can't go back and slightly wiggle the black holes or change the parameters in order to see how this would change the gravitational wave signal you receive. You also just don't know in advance what system you're dealing with. To know what experiment you're doing is going to have to be based on your observational results. And at least in the case of binary black hole mergers, so the main kinds of events being observed, there's no independent access to the target systems. You really just have the one gravitational wave signal in most cases, and that's really it. There's no sort of repeatability, and you don't have any other sort of corroborating source of information. Now, of course, in the case of GW 170817, there wasn't an electromagnetic counterpart. So there was some kind of independent access to this target system. And the question then is, what exactly does this buy us? So I'm going to take perhaps a slightly surprising turn here and start talking about historical sciences. So astrophysics is a historical science in the sense that when we observe the universe, we're observing the past. And there's some sort of resemblance to looking at geological strata, where the further away you look, the further into the past you're looking. And especially the lack of controlled experiments gives astrophysics a lot in common with sciences like geology and paleontology. Now, philosophers of historical sciences have emphasized the use of traces and methods based on traces in making inferences about the past. Now, a trace is defined as some kind of downstream consequence of a past event or entity, such that we can learn about that past entity by studying X. So think of this as sort of analogous to an observation in astrophysics. Your data, in this case, in astrophysics would be a trace. And philosophers of historical sciences emphasize that traces are evidence about the past in virtue of some kind of mid-range theory that describes dependency relations between X and Y, ways that X and Y depend on one another. And this is basically a probabilistic notion. If X had, so some variable characterizing X and some variable characterizing Y are probabilistically related. Okay, so this has some pretty clear links to some of what philosophers have said about observation in astrophysics. So Dudley Shapiro in 1982 was concerned about astrophysicists' descriptions of making direct observations of the inside of the sun using solar neutrinos. And he argued that something, in this case, the interior of the sun, is directly observed if information is received by an appropriate receptor and that information is transmitted directly, that is without interference to the receptor from the entity. So we have some kind of direct transmission from a source or a target system to a receptor where you're receiving a signal or a trace. Now, Shapiro emphasized that what counts as an observation is always relative to current physical knowledge. And what's meant by that is that you need to have some kind of theory of the source system, theory or model. You need some kind of theory or model of the transmission process, how the signal sort of gets from the source to your detector, and a theory of the receptor. So of course, this looks very much like the mid-range theories emphasized in the historical sciences. In either case, what you need is some kind of theoretical understanding of the way that your received signal or data reflects the state of the system you're interested in learning about. Now, in philosophy of the historical sciences, it's emphasized that the sort of different challenges that characterize historical sciences require at least some kind of different characteristic methodologies for approaching the science. Now, this isn't to say that observational sciences or historical sciences are completely distinct from experimental sciences, merely that their characteristic methodologies are going to be a little different. So today I'm going to be talking about two of those methodologies that are often emphasized. Now these are going to be particular to, so because I'm focused on a single event rather than an ensemble of events, I'll be talking about some methods that are appropriate to that. But you could also throw in natural experiments or quasi-experiments into the mix. So the first is sometimes called the Sherlock Holmes method, and this involves unifying traces by positing a common cause. So the idea is that this resembles the criminology of Sherlock Holmes. You've got a bunch of different clues, and you're trying to make an inference about the sort of crime or cause of those clues. So a classic example of this comes from Carol Cleland, so the famous mass extinction event at the KPG Boundary. extinction of the non-avian dinosaurs. So we have a list of traces here, the fossil record that seems to show a mass extinction event, elevated iridium levels at a particular place in the geological strata, which suggest either an asteroid impact or a period of increased volcanic activity. We have shocked quartz deposits, which indicate essentially a very destructive event, either an asteroid impact on the one hand, or this is also found at nuclear test sites. So there's this, from those three traces alone, scientists essentially confirmed the hypothesis of an asteroid impact, because you've eliminated, you've ruled out this alternative hypotheses. And then of course the discovery of the crater provided sort of further confirmation of this hypothesis. The main point is that you've got these diverse traces, and you're unifying them by positing the common cause of an asteroid impact. Part of this story is the importance of a so-called smoking gun, which is some kind of piece of evidence that clinches the case. So in this, the shock quartz deposits are here considered a smoking gun because they sort of decided the matter between the one hypothesis of an asteroid impact and another hypothesis of increased volcanic activity. And historical scientists are often guided by the search for smoking guns. And so this, in the sense, they're playing a very active role in gathering the right kinds of traces. It's not merely some kind of passive observation where you gather all the evidence and then have to make an inference. Often you're playing an active role in really going after the kind of evidence that you know will decide the case. So I think that an example of this kind of style of reasoning in the case of GW 0817 is the argument for the association between the various signals. So in particular, the argument for the association between the electromagnetic counterpart, or the optical transient, and both the gravitational wave and gamma ray signals. So this argument proceeds sort of as a series of common cause arguments. First of all, you have coincident gravitational wave triggers in two different detectors. And in order to explain those coincident triggers, there's some kind of argument to a common cause, where you posit that this wasn't caused by chance, by noise, but instead was produced by a common cause of an actual gravitational wave. Then, based on the coincidence between the gravitational waves and the gamma ray burst, there's a further inference to a common cause of both of those signals. And in these cases, both the gravitational waves and the gamma ray burst detections come along with some kind of background estimate for the rates at which these events occur. And so you can easily sort of make the calculation that it's unlikely that these two events would have occurred at the same time and coming from the sort of same direction by chance. And so thus the argument that they're associated. The third step is then to associate those with the optical transient observed following a massive observational campaign. And this is the slightly more subtle argument, because it would be very easy to say, well, we made a prediction, looked in the sky and found it in the right place. That's all there is to the story. But of course, there was no sort of equivalent observational campaign for different parts of the sky over at different periods of time. And so you're lacking here a sort of background estimate of how likely it would be that if you got half of the astronomers in the world looking at a different period of sky at a different period of time, you would have observed the same thing. So of course, AT to 2017 GFO was found within the given localization region. Of course, that's where everybody was looking. The rates of such an optical transient were estimated by using long-running transient surveys. And so this includes sort of the overall rates of transients, but it also, the background estimate also incorporates features of the observations that made it a really special event. So from this, you can estimate the likelihood of a chance spatial and temporal coincidence between all of the signals, and therefore make the sort of the argument that this coincidence was really unlikely on the base if they weren't associated with one another. And so you end up combining these three traces or pieces of evidence by positing that there is a common cause for all of these signals. So a binary neutron star merger in particular unifies these diverse traces. The second argumentative strategy that I'm going to talk about briefly is consilience. So this is when you get convergent results from independent lines of evidence. So the idea is that if you have two separate arguments relying on different assumptions and you get the same result, then you have a more robust conclusion. So we have argument one with piece of evidence one and some auxiliary conditions in virtue of which it is evidence for some conclusion. And alternatively, some other argument relying on a different piece of evidence and different auxiliary conditions. But they both produce the outcome C, then we have good reason to believe C. And as I just said, this relies on having different auxiliary conditions in virtue of which they count as evidence. So an example of this kind of argumentative strategy in the multi-messenger context comes from using both gravitational waves and the electromagnetic observations to produce independent arguments in favor of the hypothesis that the source of these these observations really was a binary neutron star merger. So on the one hand, on the left-hand side, you can make this argument on the basis of mass estimates. So if you measure the chirp mass and then do parameter estimation and figure out the component masses, it looks very much like the component masses suggest that a binary neutron star merger was the source for GW 170817. On the other hand, the various properties of the electromagnetic observations being consistent with models of kilonovae also strongly suggest the source being a binary neutron star merger. And since these are independent lines of evidence, you end up having a more robust conclusion for that this was in fact a binary neutron star merger. Okay, so I'm running somewhat short on time, so I'm just going to quickly go through some of the things that I think are philosophically interesting here. So philosophers have, it's very common to claim that historical sciences are inferior to experimental sciences due to the lack of controlled experiments. And in the context of astrophysics, Ian Hacking famously paints an extremely bleak picture for astrophysics. So part of this is to do with his sort of broader philosophical views about when we can be realists, that is to sort of literally, to think that our sort of scientific theories are literally true in describing of the world. But he also thinks that the sort of methodology of astrophysics is somehow kind of other and limited. So the idea is that it just involves bringing observations and models into line, and we can never be realist about models. So we should never be realists about cosmic entities. So two worries here. First, that astrophysics is somehow epistemically inferior to experimental sciences. And then the further sort of metaphysical concern that this inferiority means that we should be anti-realists about cosmic entities. That is to say, claims about cosmic entities like binary black hole mergers can't be taken to be literally true descriptions of the world. Now, I'm really only concerned about the first one here. The second concern is really beyond the scope. But insofar as someone like Hacking takes the epistemic concern to be justification for the metaphysical concern. If the methods that I've described in astrophysics are in fact not epistemically inferior, then this is going to cut against the anti-realism concern as well. Now, just to be a bit more concrete about this, one of the main concerns that persists with the argumentative strategies I've described is that it might just be the case that, so both of those strategies rely on having a diverse trace set. That is, you need a range of different traces in order to make those arguments work. But of course, we can worry that the available traces are at least often going to be inadequate for the task. And philosophers disagree about the extent to which this is a big problem. So on the one hand, we get arguments that past events are overdetermined by traces. So traces tend to sort of spread out and diversify over time. In the case of the asteroid impact, we had that wide range of traces even now, from which we can infer about a past event. But on the other hand, you might worry that there's a lot of underdetermination because there's a lot of information destroying processes that tend to sort of erase evidence over time. And philosopher Adrian Curry describes there being a sort of balancing act where, yes, traces spread out and diversify over time, but of course there's also these information defining processes. So we can think of this as sort of analogous to a ripples on a pond where, you know, the traces are spread out over time and you can collect more and more traces. However, they do get weaker and often disappear. In the case of astrophysics, this looks a little bit more literal than the metaphor that it is in the case of other historical sciences. But the key point is that one of the great challenges in astrophysics is, of course, collecting a diverse set of traces from which we can infer about a single source while separating it out from all of the noise from other processes. So the significance of multi-messenger observations, in my view, concerns the multiplication and diversification of traces. In multi-messenger astrophysics, obviously, it's very clear that there are these independent lines of evidence about a target system. And from this, because you have these diverse traces, this enables a range of argumentative strategies not available when traces are limited. And sort of by seeing the analogies with other historical sciences, I think it's pretty clear why this is so important. And the use of these strategies, I think, cuts against concerns about the methodology of gravitational wave astrophysics. So in the case of the Sherlock Holmes method, this sort of cuts against any concerns about underdetermination. You know, if you have a diverse set of traces, you're able to sort of rule out alternative hypotheses and really sort of narrow in on one. And consilience cuts against the concern about model dependence. So if you're concerned that gravitational wave astrophysics, the inferences are very dependent on the models, having a sort of corroborating line of access into the system cuts against that concern. Of course, we're still limited by the available theories allowing us to make inferences and the kinds of dependencies that are available between the source and the trace. So for example, if there's no dependencies between late stage dynamics of a binary black hole merger and an electromagnetic counterpart, you're not going to be able to use consilience in order to sort of overcome that worry. So to briefly conclude, I've said that one of the main challenges defining the epistemic situation of astrophysics is the scarcity or of a diverse trace set. Multi-messenger astrophysics has often been sort of perhaps hyperbolically described as revolutionary for providing independent lines of evidence about a single target system. And I think we can sort of spell this out in terms of the argumentative strategies that it enables. So on the one hand, the Sherlock Holmes arguments for unifying diverse traces about a common cause. And on the other hand, consilience arguments that essentially reassure us that nothing's going really drastically wrong with the inferences in gravitational wave astrophysics. There's a sort of bridge with more established electromagnetic astrophysics that we have a longer history with and sort of good reason for trusting. And so overall, I want to suggest that, gravitational wave astrophysics is neither so sort of methodologically unusual in terms of its situation, nor so impoverished as you might first think if you're just looking at sort of binary black hole mergers and this sort of one signal that's arriving from them. Indeed, sort of epistemically lucky cases like GW 170817 seem to provide good grounds for optimism. Thank you.
All right. Well, thank you very much, Jamie. Let's have some questions. Seeing as the next session will be followed by a lunch break, which is a kind of significant chunk of time, I think we can afford having some time for questions. So please. Oops. 2 or 3 or 4 raised hands. Wow, 5 raised hands. Gee, wow. Okay, so Ramesh, why don't you kick us off?
Okay, you hear me, right?
Yep.
Yes.
Good. So this whole business about circularity, being model dependent, etc. And I'm now talking only about the gravitational waves, forget the electromagnetic part. To me, it seems that that's probably kind of oversold, in the sense these models were created long before the detection was made, right? The theory came first. People computed these models. They came up with very detailed light curves. It's not like it's one single detection. As a function of time, it was predicted what this signal would do, and then you compare it to the observations and it fits. To me, that looks like a huge confirmation. It's not like, one trace. It's a whole trace as a function of time that has been confirmed. I would have thought that by itself is a complete vindication of the whole model and confirmation. I don't see the need for all these, questioning of whether this is enough or not. So maybe I'm just coming from the standard scientific method approach. So if you could explain why that by itself was not considered enough, where does the circularity come? That would help.
Okay, so this is a great question, and to some extent, I think that you're right. Certainly, the models were worked out in advance. In some cases, I mean, it's not like there's not sort of a fully worked out parameter space based on numerical relativity simulations, which would of course be the ideal case. But yes, there was a full template library worked out in advance. However, if what you're concerned about is something having gone wrong because your models were inaccurate, we can think about, so what happens, for example, if general relativity turns out to provide inaccurate descriptions of the late time dynamics? How would we know that was the case, given that we don't have the same kind of well worked out sort of possibility space for the alternatives? Now, on the one hand, you want to say that observing the gravitational waves for this regime would tell us it would certainly tell us if what we were observing was inconsistent with general relativity. What it wouldn't tell us is if we got a gravitational wave signal that was consistent with the general relativity for some different target system, for example. And so there could be a kind of degeneracy there. And so if it were the case that our models were wrong, it's not necessarily clear that we would be in a good position to know, because we can check that it's consistent with a general relativistic signal, but you can't sort of do the stronger test of seeing whether it favors general relativity or some alternative, if that helps.
Let's move on quickly because there's still 4 hands raised. I don't think we'll have time to go through all of them. Let's go for Gary because he's next in the line.
Yeah, just to follow up Ramesh's point, I've always taken the view that the chirp signal is consistent with general relativity, provided you accept the masses of the two black holes that coalesced, but those masses are derived from general relativity. So, you know, if you had independent measures of the masses of the two bodies, it would be a much more rigorous test. So I'm wondering if LISA, the space-based gravitational wave detector, offers a way to establish a more rigorous test of general relativity, in that it will be sensitive to systems pre-merger. And so you will have time, in theory, to examine each of the two bodies that are emitting gravitational waves before they merge, and perhaps confirm their masses, and then test that against the waves that are detected by LISA. And I'm wondering, Jamie, if you would consider that a more rigorous test than LIGO.
So I haven't thought too carefully about the implications of LISA, and so there's probably other people in the audience who have a better idea of this. In general, you know, observing the early stages doesn't always help, just because, of course, that's the point where we already are quite confident that general relativity provides a good description. But of course, if you did have really accurate parameter estimation based on the early stages of the merger, or rather the early in spiral, I think that would certainly help a lot in being more certain about the inferences you make on the basis of the late stage of the signal. Yeah, so I think that at least in principle, this could offer a way of sort of breaking the sort of circularity concern.
All right, Owen, and then Avi and Peter, but please, guys, let's try and speed up some of the questions and answers, because we're on a schedule. Owen?
He's muted.
You're still muted. There we go. Now you're unmuted.
Oh, I'm okay. All right. Sorry, I missed it. I just wanted to make two comments on your Chicxulub statements. One is, and maybe Avi was going to already make this comment, I'm not sure, that it's not at all clear that it was an asteroid. Was always stated an asteroid or a comet, and Avi and his student recently published a paper making a reasonably strong argument that it was a comet and not an asteroid that was responsible for the Chicxulub crater. And the second comment I wanted to make is that it doesn't have to be either or, that is, the extinction of all the organisms due to that may have been in part due to the volcanic eruptions in the Deccan Traps, and they may be related through the seismic energy delivered by the comet impact, which was very sizable all the way in India, being almost the antipodal point in the world, and could have set off volcanic eruptions. But that possibility is not at all well established. It's just a possibility. Anyway, that's all I'll say for that.
Right. Well, I think I agree with everything you said, and indeed, I think this sort of highlights some of the difficulties about making inferences about the past based on traces. But yeah, I think that's all I need to say.
Yeah, I just wanted to make the point that multi-messengers are useful when we don't know the source. They are less useful when astronomers tell you that they fully understand what the source is like. I mean, multi-messenger astronomy is not new. It was not pioneered by gravitational waves. We detected cosmic rays from solar flares from the sun. So we saw the sun both in light and in particles. We detected neutrinos from supernova 1987A. And that indicated that indeed we understand how neutron stars form. And of course, we detected gravitational waves as well. But you know, in all these cases, we sort of knew what we are doing to start with. And we don't need other people to tell us, oh, we detected another way, or, you know, another form of the same source, because we pretty much understood what we are doing. But I can imagine a situation where there would be a gravitational wave source in the future that looks very peculiar, that doesn't look like a black hole merger or a neutron star black hole merger. Maybe it is, I don't know, a superconducting cosmic string that you know, has a cusp or something else. And in that case, actually, that's where the detective work of Sherlock Holmes comes into play, because you don't know what it is, and then you want multi-messengers in order to figure it out. I would argue that these are the instances where multi-messengers are useful. Otherwise, it's redundant.
Right. Of course, redundancy isn't always a bad thing. I think as consilience, as the consilience strategy, I mean, that's essentially making redundancy into a virtue, making sort of increasing the confidence you already had in whatever you were doing.
Agreed.
Martin, you're muted.
Oh, I'm muted now. I tell everyone to unmute, and I'm the one that's muted. Sorry, Peter, please.
Okay, very quickly, just an observation. First, thank you for a very nice talk, Jamie. It was really nicely put together, and I like the comparison with the historical sciences, because in a way, astrophysics is also a historical science since we're looking into the past. But what I wanted to mainly emphasize was that the hacking response, that we know something's real when we can manipulate it, was originally intended as a riposte to von Frossen. And, you know, I think it should be, we should see it, or at least generously see it, as a sufficient condition for one particular kind of science in one particular situation, where it's a sufficient condition to be able to manipulate something to come to believe, to be persuaded of its reality. But it would be a crazy mistake to think that all the sciences function in the same way, that all the sciences are experimental or all the sciences are predictive. Evolutionary biology is not very predictive. I mean, the sciences have different ways of characterizing their knowledge. And it seems to me that looking into and trying to talk about the epistemology of astrophysics is a very interesting and understudied domain. So I think it's very worthwhile that you're doing it. And no reason to expect that it should look like what Ian Hacking was looking at in spraying positrons. And no reason to think it would be, you know, like evolutionary science in that the astrophysics can be more predictive than evolutionary morphology can be, for instance. Okay, that's all. Thank you very much. A nice talk and a great session.
Thanks. I completely agree with everything you've said. Certainly, I didn't get too much into the hacking, partly because you know, his later arguments specific to astrophysics have already had a lot of attention and responses, and for the purposes of today, I didn't really want to get into that, but I take the point, and I think I fully agree.
All right, well, let's thank everyone. I was perhaps a little too over generous with the questions, but I think that's part of what these conferences are for as well. So we're now running behind schedule, and I apologize to everyone. I'm the chair. I'm supposed to be, you know, handling this, but I think it was worth it. And well done, Jamie, for your beautiful talk. So now let's have Achilleas. Can you share your slides? Jamie, can you stop the share? And yeah, great. All right. Achilleas, can you share your slides? Yeah, great. Beautiful.
Yeah. So
all right.
You can see the slides and you can hear me, right?
We can hear, we can see, we can hear. We're ready to go. So
very good.
Achilleas is a BHI fellow. He's a postdoctoral fellow, and Many of us know him very well. Today he'll be talking about extreme black hole anabasis. I'm very intrigued by the title. And I would just like to mention that on his research page, one of the things that he describes his research is put holography on the astronomer's map too. So I think that's a nice sentence. Anyway, Achilleas, take it away.
Thank you. Thanks, Martin. Yeah, so today I'm going to tell you a story that I titled Extreme Black Hole Anabasis as a reference to Xenophon's adventure. This is based on this paper with Shahar and Alex. So let's begin. So the story begins with the realization that near the horizon of extreme and near extreme black holes, ADS2 arises quite universally. So the near horizon of extreme Reisner-Nordstrom, for example, is given here. This is also often called the Bertotti-Robinson universe. And you can see that it's a simple ADS2 cross S2. In the case of extreme Kerr, for example, there is this near horizon of extreme Kerr geometry neck, where you can again recognize the ADS2 piece here. So what I want you to take away from this first slide is that this is a very universal statement. It's a theorem, basically, that applies to a very wide class of theories in many dimensions with mild assumptions. So ADS2-like geometry arises in the near horizon of basically all extreme and near extreme black holes. And these are near horizon approximations, but there are also exact solutions of the corresponding theories. So the Bertotti-Robinson universe solves the Einstein-Maxwell equation exactly in 4 dimensions. The first twist to the story, though, is that there's a slogan that ADS2 has no dynamics. It started in the early days of the ADS-CFT correspondence with, as far as I know, this paper. And you can see here highlighted in the abstract, there were statements that all finite energy excitations of ADS2 cross S2 are suppressed. Later on, when Kerr-CFT was proposed, similar calculations were elevated to a conclusion that went to the title, no dynamics in the extreme Kerr throat either. And more recently, even mathematicians have been proving rigorous results that could go under the title ADS2 has no dynamics. So that could be the end of the story, but it's not. And the story continues. So let's take a wider, appropriate for the BHI perspective on talking about dynamics of ADS2. So it is true that the back reaction in asymptotically ADS2 spacetimes is problematic. So for example, if you ask yourself, what if I start with a linear solution for a scalar field phi on ADS2 cross S2 and let it back react on the geometry? Is this going to lead to a nonlinear solution of the Einstein-Maxwell-Klein-Gordon equations of motion? The answer is no, if you include in your assumptions an insistence on having an asymptotically ADS2 cross S2 spacetime. So for example, if you impose Dirichlet boundary conditions on the ADS2 boundary, the back reaction of that scalar on the metric will destroy these boundary conditions. However, if you take the point of view that this ADS2 cross S2 is just a near horizon approximation of extreme Reisner-Nordstrom, then we know that the back reaction in asymptotically flat spacetimes makes perfect sense. So if you ask the same question, start with a linear solution for a scalar phi, put it on the extreme Reisner-Nordstrom, whose near horizon is ADS2 cross S2, and let's say this field has order epsilon to the 1/2. You let it back react on the geometry and you ask yourself, does that extend to a nonlinear solution of the Einstein-Maxwell-Klein-Gordon equation? And the answer to that question is yes. And we actually know what is the endpoint of that nonlinear evolution. If you do the full back reaction, the endpoint is a near extreme Reisner-Nordstrom with a deviation from extremality given by this formula where Q is m square root of 1 minus a constant that is of order epsilon. So this has been verified, for example, numerically in great detail in this paper. So the takeaway message is that the connection of ADS2 with the asymptotically flat region of black holes does allow for a consistent back reaction. We know that from what happens, for example, to the extreme Reisner North. So now the question is how, and we need to understand how, and what are the correct boundary conditions. And this is going to be the purpose of this talk. So let's begin in the vacuum case. So let's not put in the matter for the moment. So let's just consider electron vacuum. Begin with the Bertotti-Robinson solution. So this is the first line here. This is an exact solution in 4-dimensional Einstein-Maxwell. And let's consider its spherically symmetric perturbations. It turns out that the solution is fully characterized by the perturbation to the theta-theta component of the metric, because H theta-theta is actually gauge invariant under diffeomorphisms. So the full content of the linearized solutions around Bertotti-Robinson is contained in H theta-theta. And as we can see here, the solution is a 4-parameter family of solutions, 4 parameters being phi 0, A, B, and C. It's easy to see what phi 0 is parameterizing. So the Bertotti-Robinson is a 1-parameter family of nonlinear solutions with a radius of ADS2 and S2 being let's say M here. So you can always perturb it by sending M to M plus delta M and go towards another Bertotti-Robinson with a slightly bigger radius. And so phi 0 is just doing that. Phi 0 is 2M times delta M. So for the remaining of this story, the main hero is the remaining part of the solution, which I'm going to call phi. Phi is just AR plus BRT plus CR times T squared minus 1 over R squared. Okay. So this is our hero, and let's study what he does. So the background, the Bertotti-Robinson solution, has a lot of symmetry. So in addition to its spherical symmetry, there is also the symmetry associated with its ADS2 factor. That's the SL2 symmetry. And that consists of time translations, dilations, that's H and D here, and special conformal transformations. On the other hand, the perturbation phi breaks these symmetries. Namely, if you act with the SL2 on phi, A, B, C get rotated by these transformations. I should say that each term in this solution phi preserves one and only one of the SL2 symmetries. So the first term preserves time translations, second term dilations, third term special conformal transformations. But if you think about it carefully, you can identify an invariant quantity. So the SL2 invariant quantity is this mu, which is kind of determinant B squared minus 4AC. So that remains invariant under SL2 transformation. And if mu is equal to 0, then I can use SL2s to bring phi to, say, this basic phi is equal to 2R solution. On the other hand, if mu is positive, I can do SL2 transformations to the general phi to bring it to this minus square root of mu times RT. Now, these SL2 breaking solutions phi are not asymptotically ADS2 across S2. Okay. So what are they? So that leads us to the discussion of these Anavasis perturbations. So that begins with the understanding that the Bertotti-Robinson arises from two physically distinct near horizon, near extreme scaling limits, lambda goes to 0, of Reisner-Nordstrom. The first limit is as follows. So begin with an exactly extreme Reisner-Nordstrom, Q is equal to M. Do a coordinate transformation to put the black hole horizon at R is equal to 0. Then extreme Rn takes this form. Now think about this as an expansion in lambda, as a series in lambda. At order 1, what you get is the Bertotti-Robinson solution in the so-called Poincare coordinates, is what we had before this. Now, this is the sense in which Bertotti-Robinson arises as a scaling limit of Reisner-Nordstrom. Because this is an exact solution of the nonlinear Einstein-Maxwell equation in itself, we are guaranteed that the order lambda correction in the series will be, by definition, a linear solution of the Einstein-Maxwell equations around this background, the Bertotti-Robinson. And so if you look at the theta-theta component of that perturbation, and just expand this term in front of the d omega squared, you see that h theta-theta is 2r. So this is the SL2 breaking solution with mu is equal to 0 that I was previously calling phi is equal to 2r. And I'm calling this the Poincare Anavasis solution because what does Anavasis mean? You know, what it does in this context is this perturbation begins to build the asymptotically flat region of that extreme Reisner-Nordstrom. So what we see here is that the nonlinear solution obtained from the mu is equal to 0 perturbation of ADS2 cross S2, when back reaction is fully taken into account in the Einstein-Maxwell theory, is the extreme Reisner-Nordstrom black hole. Okay, now let's look at the second limit. In the second limit, you begin with the Reisner-Nordstrom, but you begin with it away from extremality. You set Q is equal to M square root 1 minus lambda squared kappa squared. And you use again coordinates that would put the black hole horizon at rho is equal to 0. So then Reisner-Nordstrom takes this form. Focus again on the d omega squared term here. If you do the expansion in lambda for this, at order 1, you will find Bertotti-Robinson again, but in this so-called Rindler coordinates. So this solution here is again Bertotti-Robinson in different coordinates. What you get at order lambda is, again, by definition, a solution to the linearized Einstein-Maxwell around this background. And looking at the h theta-theta term, what this is 2 times rho plus kappa. Now, I said this is Robinson-Bertotti in Rindler coordinates. Let me prove myself. So here's the transformation between the Rindler and the Poincare coordinates that would put that Rindler form for Bertotti-Robinson to the original Poincare one that I was displaying in the beginning of the talk. So here's a transformation between tau rho and TR. You also need to accompany it with the appropriate transformation of the gauge field. And this is shown in the Penrose diagram here on the right. So this is a Penrose diagram of global ADS2 with every point being an S2 here, actually. There are 2 time-like boundaries. The big triangle, the big wedge, is covered by the Poincare coordinates, TR. The small one is covered by the Rindler coordinates, tau rho. The important thing for this talk is that this transforms the h theta-theta Rindler analysis that we got in the previous slide, this one, to minus 2 kappa times RT. Now this, in terms of our SL2 invariance for phi, is a solution with mu positive. Square root of mu is 2 kappa. And what we just saw is that what this solution is doing is it begins to build the asymptotically flat region of a near extreme Reisner-Nordstrom. And this actually can be can be generalized. The more general statement is that if you have any solution phi with any ABC here, as long as mu is positive, you can always map it to the Rindler analysis, this one 2 times rho plus kappa, with square root of mu being 2 kappa. So what is the takeaway message? The takeaway message is that the nonlinear solution obtained from the mu greater than 0 perturbation of ADS2 across S2, when you take into account back reaction fully in the Einstein-Maxwell theory, is the near extreme Reisner-Nordstrom black hole with Q is equal to m square root 1 minus mu over 4. Okay, so these are the analysis perturbations. So let's now use them to define this thing I'm calling the connected ADS2 cross S2. So I'm defining connected ADS2 cross S2 to be the geometry you obtain by adding analysis perturbations to the Bertotti-Robinson solution. An alternative way to think about this is that this addition of analysis perturbations is a choice of boundary conditions such that you can have a consistent back reaction calculation in an ADS2 cross S2 throat that actually maintains its connection with the asymptotically flat region of black hole. So for example, suppose you want to do the back reaction calculation with matter. So throw in to the connected ADS2 cross S2 a matter pulse. So here's a null pulse, a delta function pulse with some small energy epsilon. Epsilon is a small parameter here. And this is a stress tensor for the matter that you would add to your Einstein-Maxwell equations. Now, when epsilon is small, we can easily solve the order epsilon Einstein-Maxwell matter equations around Bertotti-Robinson and find what is H theta theta in that case. So H theta theta in that case is given by this formula here. So as you can see here, both before and after the pulse, for V less than V0 and V greater than V0, the solution is of the vacuum type that I previously, the vacuum type that I previously discussed. So this piece, as well as this piece, is actually of that general type. But the question is, what are the correct boundary conditions for this back reaction calculation that you're trying to set up here? So naively, if you had the completely decoupled ADS2 cross S2, you would say that for V less than V0, I want H theta theta to be 0. But that's not correct. So if you're thinking that if you want to do the calculation in a connected ADS2 cross S2, what you should do is you should say, if I imagine that this ADS2 is the near horizon of an extreme Reisner-Nordstrom, then for V less than V0, what you should pick for the boundary condition is that H theta theta is actually this Poincaré analysis 2R. If you do so, then you do indeed get, after the pulse, a solution, given here, H theta theta is now 2R minus this piece, which now has an invariant SL2 quantity mu, which is positive. It's now, for this solution now, mu is actually equal to 4 epsilon. And so what this means is that now you can map this solution to the basic Rindler analysis, H theta theta equal to 2 times rho plus kappa, with kappa equal to square root of epsilon. Notice that this would not be possible if you had started with the wrong boundary condition for a completely decoupled ADS2, H theta theta equal to 0. If that was the case, then after the pulse, you would get something which is still a mu is equal to 0 perturbation. So with this correct boundary condition, you get the picture that is satisfying and correct from the Reisner-Nordstrom point of view. That is, if you throw a pulse of energy epsilon small into an extreme Reisner-Nordstrom, with Q is equal to m, what happens is the horizon shifts and the black hole becomes now near extremal with Q equal to m square root of 1 minus epsilon. precisely the deviation that we know, for example, from numerical studies. This is shown also in this picture here on the right. So in that Penrose diagram, I don't know if you can see it. I'm putting a dotted boundary here on the ADS2 to indicate that this is an approximate ADS2 that is connected to the asymptotically flat part. The pulse enters here at t is equal to v0. This is a null pulse going on here. The solution before the pulse in this region is h theta is equal to 2r. But after the pulse, it is given by this equation, which you can map to the Rindler 2 times rho plus kappa in this shaded Rindler patch, and that is connected to the near extreme, to the asymptotically flat region of that near extreme Reisen-Nordstrom with q is equal to m square root of 1 minus epsilon. Okay, so let me conclude by reminding the two basic things that we defined in this talk. So we defined analysis. That's back reaction that destroys the ADS2 boundary and builds asymptotically flat region of extreme and near extreme black holes. And the other thing is a connected ADS2, which is defined as the geometry you obtain by the addition of such analysis perturbations to the exact solution, say ADS2 cross S2. Alternatively, this is equivalently can be thought of as boundary conditions for a consistent back reaction calculation that you can do within the throat only. So that's the end of the story, but I have a few minutes left, so I may do a couple of quick remarks for some expert holographers who might be in the audience. So if you know a lot of holography, you will ask yourself, what is the dual of this analysis in ADS-CFT language? The dual of this is that you have to follow an inverse RG flow from IR to UV along an irrelevant deformation of your boundary field theory, which does not respect ADS boundary conditions, though. This is something rather unusual in ADS-CFT. It's not getting a lot of discussion. Historically, of course, ADS-CFT was discovered as the limit from string theory in asymptotically flat. But in the spirit that ADS-CFT is a self-consistent theory in and of itself, even if you consider irrelevant deformations, you often restrict yourself to considering ones which will respect the ADS2 boundary. But things have come a full circle, and there is at least one body of work by this gentleman here, started in 2017, where there is a specific deformation of a two-dimensional conformal field theory that is a single trace operator that goes under the name TT bar, which is solvable and they can follow it. And what it does is it does destroy the ADS3 asymptotics and builds an asymptotically flat with linear dilaton exterior. I should say though that nothing that I said in the talk before the end depends on holography. Everything I said is completely general for the gravitational story that will be true for all extreme and near extreme black holes. The other question you might ask yourself is, what about JT gravity? So that's a good question as well. So in terms of JT language, that phi that I was talking about, the main hero of the story, is the dilaton in the JT theory, and it solves the JT equation of motion on ADS2. The invariant nu is the ADM mass of the 2D black holes in JT gravity. And you can think of the connected ADS2 as a nearly ADS2 in that language, with its SL2 broken appropriately to maintain connection with the asymptotically flat region. I should say, though, that it is often said in the JT literature that nearly ADS2 is associated with deviation from extremality. Not necessarily so. As we saw, you can break the SL2 with mu is equal to 0 only in order to build the exterior of an exactly extreme Reisner Nostrum. I guess I'll end here. Have some questions.
Thank you very much, Achilleas, for a wonderful talk that was also very well timed, which was wonderful. Well done. Right, so questions, comments, please go ahead. I see that Ramesh has already a hand up.
Yeah, I didn't follow all the details, but while I was listening, it seemed to me that what you're describing is a version of a Vaidya solution for Reisner-Nordstrom. Is that what it is, the pulse moving in?
Yes, that is correct. So it is to be understood that this pulse has to be arranged to come in and enter the near horizon of the Reisner-Nordstrom. So we are in the middle of that kind of calculation. You can broaden this delta function pulse a little bit, and then set up so-called matched asymptotic expansions to have some low energy waves sent in from flat infinity, which will have this effect that by the time they enter the near horizon ADS2 region of the Reisner-Nordstrom, they will be, a narrow Gaussian like this. And then, yes, in the Vaidya sense, what you expect is that if you start with an extreme Reisner-Nordstrom, you make a near extreme.
Right, but then you can now consider a Vaidya solution in a full generality, right? For any Reisner-Nordstrom, not necessarily extremal, and you should be able to get a whole series of these kinds of solutions.
I'm not sure what you are referring to. The whole series, you mean with, say, outgoing?
No, all ingoing only, but ingoing, I can have a pulse, not necessarily going into the extremal case, but in any Reisner-Nordstrom, and I can get a whole family of solutions where you're basically changing the asymptotic boundary condition.
Right, you could, for example, throw this into a near extreme Reisner-Nordstrom with some temperature and see how you get the temperature raised a little bit.
Exactly, yeah, that's what I was thinking, yeah.
Right. That should be possible.
I had a question, but perhaps I'll wait until other people. Does anyone? Right, okay, I'll just ask my question. What you might have expected this from me, but what would you like mathematicians to do with this? Or what would you like to see done from the mathematical perspective for these kind of guys?
So there is an interesting thing that Aretakis noticed, right? That these extremal black holes might have a kind of black hole, a kind of hair.
Yeah.
And this is a generic situation where you throw in something and you make a near extremal black hole. But in this numerical work here, for example, it was observed that there is a special class of initial conditions, a very fine-tuned class of initial conditions, which you can arrange such that even though you're perturbing this extreme Reisner-Nordstrom, this Aretakis instability persists for all times.
Mm-hmm.
And it's something that modifies only the ADS2 region. In the exterior, it's still exactly extreme Reisner-Nordstrom. But this, they saw numerically that the nonlinear evolution is a space-time which has these Aretakis constants turned on forever, kind of black hole hair. And they define this thing as a dynamical extreme Reisner-Nordstrom. So I would like to understand that better. I would like to understand what is that initial data that produces this thing. Is it really appropriate to talk about it as black hole hair? And how to understand that in ADS2 only, because it is captured by the ADS2 only.
Okay, thank you. Andy has a raised hand.
Yeah, just as a comment on that last question, they are now saying, right, in the Sarataka stuff, that there's an effect on the geometry out at null infinity, I think.
They are, yes, that's true. But at the same time,
I don't fully
I mean,
understand.
if it exists, if it's only at null infinity, it's
Not
sort
at-
of the mirror of what is at the horizon.
I see.
So yeah, everywhere outside null infinity and on the horizon, space-time is exactly extreme Reisner-Nordstrom. But on the horizon, there are these Artakis constants which are not decaying and being conserved. And there is a dual of that at null infinity. They do say those things, yeah. So that would have to be understood, yeah.
Yeah. So my question was on your comments at the end. How are we supposed to think about RG flow in 0+1 dimensions? What is that?
Yeah, these comments here are in 2+1 dimensions. So this story is ADS3 CFT2.
But yours would be ADS2, right?
Mine would be ADS2. I don't know. I haven't thought about that. I mean, this should be, yeah. I mean, some kind of SYK deformation that would. What would it be? I mean, I don't know. I mean, I don't have.
I'm just wondering. We don't have infinities and.
Right. I mean, this is a quantum mechanics. It's not. Yeah. How do you even talk about RG flow? That's what you mean, right?
Yeah.
I don't know. This comment was more general about ADS-CFT.
Oh.
You know, in the sense of breaking the ADS boundary to bring back the asymptotically flat geometry, and that has been achieved to some success in these papers for ADS3 CFT2. I don't know what you would do for ADS2. I mean, there are some papers which talk about a TT bar deformation of
quantum mechanics
for JT, you know, within the context of JT gravity and for ADS2, but I haven't studied them in detail.
Thank you.
All right. Well, has anybody got any final questions before we take the lunch break? No. Well, let's thank Achilleas again for a beautiful talk, and we'll see you all at 1:30. Bye bye, everyone.